Ladies and gentlemen, please welcome to the stage Jason Benedict, Vice President, BioVia Research and Development.
Today, I have the great honor to welcome Professor Byron Pipes to Science in the Age of Experience. Professor Pipes is the Executive Director for Advanced Composites Manufacturing and Simulation Center of Purdue University, a member of the National Academy of Engineering and of the Royal Society of Engineering Sciences of Sweden. Professor Pipes has been at the leading edge of innovation in advanced composites for many, many years, publishing well over 100 papers on this subject area. Professor Pipes, please come give us a vision for advanced composite simulations in 2040.
Good morning. Thank you. Good morning, all. What an inspiring set of lectures to follow. The wonderful future that simulation brings to the quality of human life. I think I am at awe of my colleagues and their presentations and all of what we're learning and how we're using simulation today. I want to share a few thoughts with you focused in perhaps an area that some of you know and some of you have experienced. I'm going to talk about high-performance composite materials as an example of simulation and where this is going and why and how we deal with the future of simulation and engineering in general. Let me start by the choice of the title, because innovation is important to us all, but what will be the language of innovation in the future? And the answer is simulation, no question about it. It is going to be that which glues us all together. In many ways, these two talks, I think, illustrate an extremely important point, that the knowledge base that we have created in times has been recorded in books and curves and graphs and information. In the future, our knowledge will reside in simulation tools themselves. This is where the future is going, and I want to show you a couple of examples as we go forward. First, let me tell you a little bit about the industry that's evolved since 1960, when two inventors in the world discovered that they could take essentially a common polymer fiber and turn it into the world's strongest material, a carbon fiber. That carbon fiber was then introduced, and people said, it's so light and strong, what could we make of this? 50 years later, we're flying in airplanes which are entirely composed of this material, no metallic structural components at all in the wings, the empennage, and the fuselage. Let me just give a few shout outs or thank yous to the team that I represent. Here you see a group of faculty and engineers. What's not seen is the number of wonderful graduate students that are involved in this group. I want to call special attention to Jan-Anders Monsen, who we've recently attracted to Purdue to join us from EPFL in Switzerland. He and I are partners today. We have a partnership, and perhaps we're the two people in the world who've spent most of our time thinking about how these new products will be manufactured from these materials. We live together in a building called the Indiana Manufacturing Institute. Many people refer to it as IMI, as the acronym would be. This is a building in which the university and industry meet. And it's actually not on the campus. It's in the research park at Purdue, just north of our campus, but within easy bicycling distance. I want to take a moment to think a little bit about what has happened just since I entered the field of composite materials in 1968. Look at the increase in power that we have today at our disposal. Now understand, 50 years ago, we were thinking very much about how would we build an aircraft from these materials, and we were thinking about them in all of the processes, procedures, engineering, discipline was required to be developed. So I asked myself at the time, and others did as well, how will we do this? How can we model this problem? How can we engineer it? The answer was not very satisfactorily, I might add. Computers were relatively small at that time. And look at the increase in power, 1 billion times over this 50 years. So what technology has increased the most during this time? It is simulation power and the tools that drive that innovation. Just to put this in perspective, if you've not actually ever seen a carbon fiber, they are so small, they're very difficult to see actually. Smaller than a human hair quite a bit, of the order of 5 microns, and yet these strong and stiff materials provide the foundation for a class of growing materials that one has available to them. Take a look, for example, at this plot of stiffness versus strength based on density, and you will see that the carbon fiber composite consisting of part carbon fiber and part polymer is of the most strong and light and stiff materials in the world. By the way, BIOVIA, the tool that here is at the very base, if you will, starting at the nano level and the molecular level, can in fact produce or predict the properties of many of these material systems today, and that capability is growing. While I'll not illustrate that concept here today, it is at the foundation of much of what we have done, both in fiber synthesis and in polymer synthesis and their interactions. So there is science at the base of all of this engineering, as you might expect there must be and will always be. What is this technology produced first? Well, in this country, we perhaps spend more money in defense of our nation than we spend in anything else, including health care, although the two are beginning to rival one another as they should, in my opinion. I hope there comes a day when we spend all of it in health care and human prosperity. But the first application of these materials was in defense. And we've gone through a process where we learned how to manufacture them, we learned how to deploy them. That took some years. Following that, many of you may have flown here on the 787 or the Airbus 350, both of which are all composite. And today we're introducing an all-composite wing in the 777X airplane, soon to be released and, if you will, roll off the manufacturing floor. This airplane has a wing that's so large it has to have a hinge at the end so that the plane can roll up to the gate for the passengers to either enter or depart. But it's an enormous accomplishment on the part of the Boeing company, and that is underway. This gives us greater efficiency. Flights now can take place with less fuel and less pollution, as the case may be. From that has come leisure products. Interestingly enough, as we thought about the application of these materials and the future, the leisure product industry immediately stepped into that opportunity. And carbon fiber now provides the primary material form for the America's Cup applications you can see here. Not only is the hull of the structure, but all of the mass structure, the wing, if you will, the sail, are all carbon fiber. And this competition has led the way in teaching us how to drive the technology to its limits. I'll speak more about that in a moment. Next came automotive, where lightweighting, reducing the weight of a vehicle to extend either the range of the electric car or to make the fossil fuel car more efficient, has been a development ongoing now for some years, but it's accelerating today. And I can predict really that as the electric car becomes the mode of transportation of the future, you will see many more applications of this carbon fiber system. I love the picture here showing two individuals who are able to carry by themselves the entire structural frame for the car, in this case the i3 by BMW. An extraordinary accomplishment, but notice that this vehicle is also manufactured in the rates in which automobiles must be manufactured in order that hundreds of thousands of units can be produced in the time necessary for the product to be supplied to those who wish to purchase it. Whereas aircraft, as we well know, can produce products that are produced in days or months. Cars have much shorter time frames for production. This is a subject that I'm going to return to in just a moment. As a matter of fact, if you look back over the years of what has happened in this field, and this data is a little bit old, but frankly the curves remain for the next decade, they just continue, such that today we produce over 100 million pounds of carbon fiber in the world is utilized in the products that are being consumed primarily in the automotive and the leisure product industry, all across golf shafts, tennis rackets, and on into wind energy and the like. One comment is that as we had the major invention of these materials in the space era, their costs were extraordinary. But as leisure product began to enter this market, the cost began to come down as the volume went up. That cost volume ratio correspondence, if you will, of clearly that economic principle continues to hold in this area as well. Now, as we think about, as you make a business of any of these products, aerospace is a good example where we spend numbers of years of investment in the development of the materials and the design, after which we have a considerable number of years of market in which profit can be extracted to pay back that investment. If you look at the other end of the extreme, and that is the consumer electronics industry, you see that products turn from the design phase to the market phase in sometimes months. The contrast is interesting, and it suggests to us what is coming in aerospace as well as automobiles. We must turn the technology development time faster in the future if we're going to meet the needs of our population for these products. And now, as you'll see in a moment, some of the industries have discovered this and are understanding what's going to happen and what needs to happen. Interestingly enough, the composites industry, as we know it, came from aerospace. It went then to leisure products, and now to automotive. It'll be interesting to see, as you'll see in a moment, can it go in the reverse direction? Can we use the rate methods that we're developing on automotive and leisure products in aerospace, and with the same level of confidence we do today? I think the answer is yes, but let me give a couple of examples. Greg Heislip is the Chief Technology Officer of Boeing, and we recently met with Greg he came to Purdue to give a talk on what he was doing, and he appealed to us that he has this challenge. Perhaps the whole aerospace industry has this challenge, which is the demand exceeds the ability to produce in the time frame which we have. We must accelerate this manufacturing process. Just look at those numbers. A backlog of 5,000 orders, the ability to produce much less than that. How do we meet that objective? And he appealed to us. Spend some time thinking about this. Come back to me with some ideas, and we're doing that. By the way, the supply chain that he had for the 787 is a global supply chain. Now let me return to the word language for a moment. And I don't mean English, I mean simulation. What is it that could possibly tie this complete supply chain together in an efficient way? There's really only one answer, and that's simulation. It has to be the answer. But is it? Well, not yet, it isn't. As a matter of fact, as I'll state in a moment, there's some challenges here. There's some challenges to access. There's some challenges to need. I'll come back to that shortly. So, if simulation is going to be the language of innovation, and if these products are going to be supply chain based, large numbers of suppliers worldwide, lots of different cultures and languages, how do we glue them together? The answer is the supply chain must have access to this language and to this set of simulation tools. Today, OEMs have it. They do. They helped generate it. They drove it. Material suppliers and tier ones modestly have it. Tier 2, tier 3, they don't have it. They need it. They must have it. So how do we preserve a digital thread if people or organizations within that digital thread don't actually have the thread? This is the challenge, I think, that we are faced with today. So let's look at a vision for how that might be if they had access to it. If they had everything easy and in their hands and had the educated human talent and engineering talent to use it. Well, we could begin to deliver manufactured informed performance, not the performance of something ideally designed and perfect, but that which was manufactured the way it must be manufactured and the performance that comes from that. We need to do that. We must have a digital twin in manufacturing, not just a digital twin in geometry. I thought the example just now about the digital twin of the human skeleton. You must actually model what is there, not what you'd like to be there in the design process. So we need the Composites Virtual Factory. If we have that, well, how do we deliver it? How do we deliver it to the supply chain? I want to show you an example that we're developing at Purdue that we think is maybe an early example of what you will do as this goes forward in what we're calling workflow apps. Think phone apps, and now you have the analogy that I'm thinking about. A single, if you will, focused solution by the simulation code that you're using. It doesn't solve everything, it solves only what I need. If I'm looking for restaurants, I use my phone to find the one I need. If I need to solve a problem in manufacturing, I need to focus on the specific problem and have everything I need. That's what we're calling apps. And I want to give you one example of an app that we have developed at Purdue. We have 4 finished in manufacturing processes. There are an infinity to do, but we have identified 12 major ones that we think are the right ones. that will capture all possible manufacturing methods. Of course, that's not possible, but at least some have not been invented yet. And I'm going to choose prepreg platelet compression molding today as an example because it illustrates how one must integrate several competencies to produce these apps. On the right, you see the app for additive manufacturing, additive 3D. You see it for injection overmolding, overmolding 3D, high pressure resin transfer molding, and so on. The example we're going to go through today is compression molding. Why is this important? Because in manufacturing, I start with a manufacturing process to produce something. I do not start with all possibilities. I must choose among these, and I must model all aspects of that. Here I've identified additive 3D, prepreg 3D, and you can read those. The last of which is cost 3D, meaning cost modeling must be integral into manufacturing, as we know. I want to say that the 3D experience and the world of the Composites Virtual Factory are in many ways coincident and in many ways require one another in structure. In the first case, the people that are necessary for that are illustrated by 3 of our engineers observing and participating in a project related to a specific manufacturing process here. And then the simulation tools themselves that support those people. That is the Composites Virtual Factory of the future. It's delivered, and the version that we're working on, the Composites Virtual Factory HUD, it's delivered by the cloud, and it's delivered to a browser-based system so that individuals can, no matter where they are in the food chain, if you will, the supply chain, have access to these capabilities. Let me take one. And I know that not everyone in the room is a composites expert, but just take a moment and follow with me. Platelet composites, we start with a prepreg tape. We actually have continuous fiber in that tape. It's very much like fiberglass reinforced tape, if you will, that you wrap a present with. But this is carbon fiber. We cut it into small pieces. We then mold it into parts. The question is, can you follow that molding, develop those internal geometries, very much like the internal geometry of that orthopedic structure? Can you model that process? And the answer is yes, but one must start with some relatively sophisticated mathematics. Here we have the tensor for viscosity of those systems. It's a 4th order tensor, and it's related very much to the orientation of the fibers in the system. So we must follow that orientation. And here I show you some spherical particle hydrodynamic simulations within Abacus, perhaps never intended for this purpose, but is now showing that we can follow the platelets as they are cut in the part. We can follow them. We can follow their orientation state. So now we have more complexity inside the material than the geometric complexity that has been described so far. That geometric complexity internal is mapped into the real part. And now we ask the question, how good is that simulation? Let's compare a CAT scan for one of the vectors, if you will, to the simulation. And as you take a look at this, we showed this to Boeing the first time. We didn't show them which was the molding simulation and which was the actual CAT scan. And they couldn't tell the difference, neither could we, frankly, until we found the notices there of which they were. And then if you take a look at plotting around the molded in hole, if you will, you see how good that simulation is, even in very discrete points within the structure. We can simulate very complex problems in these systems. Can we do the same thing with the strength characteristics once we know the internal microstructure, again, we go through some internal capabilities in Abacus, composite damage modeling, and we construct the virtual image of the real material, and then we can carry out a virtual tensile test of the material. On the right is the virtual part, and on the left, you'll see the red, gold arrow there. That is the real part, and if the question is, did it fail at the right point, and does it have the right morphology? Answer, yes, yes, this works. So you can apply that then to the complex structure that's shown here. I want to spend a few moments then talking about what's coming, and I want to talk about what NASA has done recently with its multi-scale modeling and simulation vision for 2040. I like this idea very much. In fact, 2020 seems to have been the time I was looking forward to in much of this. Well, that's coming just around the corner, so it's very appropriate that NASA be thinking about what is the simulation of the future? What should it look like? And it's very interesting when they describe this vision, what this world's going to look like. I draw your attention to what is the end characteristics of these materials, of this simulation capability. Accessible, adaptable, interoperable, robust, traceable, and user-friendly. All that sounds just right. How good is it today? What are we doing? Well, if it's browser-based and cloud-based, it's accessible. Can it be adaptable? Well, new apps, new needs are coming daily. They must evolve. You must evolve. Interoperable, multi-vendor interaction is essential if you're going to carry out app-like simulation. Traceable, the digital thread, the digital pipeline, the product life management. These are all going to be the essence of that. User-friendly. It means tools focused on specific needs. All of the supply chain needs this. We need pervasive tool learning all across the board. Engineers who are sitting in place today still must learn all of this because it's coming at them at a very rapid rate. And finally, we need to validate these tools. So the virtual laboratory is a thing of the future, or one might even say the virtual laboratory is of the present. So what are the challenges that this calls? What must be due in the next few years? Well, these innovations in the tools themselves, that is to say, the modeling of the physical and chemical phenomena in these manufacturing processes, will continue to develop. We must adapt them and adopt them. These innovations will largely come from small businesses. They won't necessarily come from our large corporations or from us, who even universities. We're going to see more, and still do see routinely, more coming from small and small groups of people. The systems that we're developing have to have the agility to absorb those, take them, and mature them rapidly. The continuity of this digital thread, how do we make sure one code to the other, that thread is preserved even within the centralized program? So we need to have data fidelity assured. If we're going to use this data, this simulation, to certify flight, human flight, we need to understand that and hold it in the same way that human health needs health records. We must have that in our vehicles of the future. All the manufacturing processes must be captured. We must capture the variability of the material. And of course, we're seeing that additive manufacturing is demanding an entirely new level of detailed information and process simulation. So in summary, I think I would say to you that I believe I've proven, to myself at least, that simulation is the language and will be the language of manufacturing innovation, that this end-to-end simulation focused in applications, I call them apps, is a coming trend, that our ecosystem of 2040 will not only include accessibility, adaptability, interoperability, traceability, user-friendliness, but pervasiveness. It is going to be throughout everything. I want to bring attention to the sponsors that have been so generous in their support to us here at Purdue. The Boeing Company, Dassault Systèmes. I didn't say much about our Institute for Advanced Composites Manufacturing Innovation, of which we are one of the team members, but that institute has done much to drive this field. And I want to say that were it not for Dassault Systèmes' support of IACME, we would not have had the kind of successes that we're having, in which industry is now benefiting by so substantially. I want to thank you very much for your attention.